A train cuts through the heart of the most ruthless desert on Earth. Below it, nothing. No roads, no rivers, no life. Just billions of tons of shifting sand stretching to the horizon in every direction. Ground temperatures hit 70 degrees Celsius in summer, hot enough to kill an unprotected person in hours. But this train doesn't care. It isn't on the ground. It's flying above all of it, gliding along a concrete track elevated high above the sand, cutting through a desert so deadly, the people who named it thousands of years ago called it, "You go in, you don't come out." This is the Taklamakan Desert Railway, and it is the most jaw-dropping construction project ever attempted in desert engineering history. Here are the numbers that will stop you cold. The railway stretches 2,685 kilometers, longer than the entire U.S. East Coast from Maine to Miami. It runs elevated on 11,000 concrete pillars above sand. It took 12,000 workers a full decade to build. It cost $3.5 billion, and every single piece of it, from the steel rails to the concrete piers to the laser-guided installation systems, was engineered, financed, and delivered by one country, China. But before you ask how, you need to understand why. Because this railway isn't just about concrete and steel. It's about what's buried underneath that sand. And what China is really building here will shock you. Before you understand what China built here, you need to understand what they were up against, because the name alone should have stopped them. In the ancient Uyghur language, Taklamakan means one thing. You go in, you don't come out. And for most of human history, that wasn't poetry. It was a fact. Entire Silk Road caravans disappeared into it. No trace, no survivors, just sand. And the sand here isn't like any desert you've seen. It's alive. The dunes don't sit still. They migrate. Driven by winds that arrive without warning, entire dunes shift position, swallowing whatever was built on them. Roads buried overnight, structures consumed within months. The desert doesn't just resist construction, it erases it. But the moving sand isn't even the worst part. The temperatures are in a completely different category of brutal. Summer ground surface hits 160 degrees Fahrenheit, not air temperature, the sand you're standing on. Standard concrete cures too fast and cracks. Machinery overheats and fails. Then winter arrives and that same ground drops to -13. A swing of over 130 degrees Fahrenheit between seasons. That destroys steel. It destroys concrete. It destroys everything. So why did China even try? Because of what's underneath that sand. Buried beneath the Taklamakan sits one of the largest untapped deposits of rare earth minerals on the planet. Neodymium, lithium, cobalt. The raw materials inside every EV battery, every smartphone chip, every missile guidance system on Earth. The materials the entire 21st century technology war is being fought over, sitting completely unreachable because nobody could get into the desert to access them. Nobody except China. And here is exactly how they did it. Before we get into how they did it, you need to feel the scale of what we're actually talking about, because the numbers here are the kind that your brain initially just refuses to accept. The Hotan-Ruokyang Railway, the key section of this project, runs 890 kilometers through the southern edge of the Taklamakan. That single stretch cost $3.5 billion and took a decade to complete. But here's the thing, that's only one piece. The full Taklamakan Desert Loop stretches 2,685 kilometers, longer than the entire U.S. East Coast from Maine to Miami, a complete circular railway system elevated above shifting sand, running through the heart of the most hostile desert on Earth. To hold it in the air, engineers built 11,000 concrete pillars, each one between 16 and 50 feet tall, lined up one after another across hundreds of miles of open sand. From a distance, it looks like a concrete centipede marching to the horizon. Up close, it feels like standing in a forest of skyscrapers. And here's what makes that number even harder to believe. 65% of the entire line runs elevated, not along the ground, not through tunnels, floating. Exposed to every sandstorm, every temperature swing, every weapon the Taklamakan throws at it. 12,000 workers, a full decade. And when it was done in June 2022, it became the longest desert railway ever built on Earth. And when China completed this, the Western media said nothing. No front page, no breaking news. China built the engineering equivalent of a railway through the Sahara, quietly opened it, and moved on to the next project. And that silence, that complete lack of acknowledgement in the West, might be the most revealing detail of all. But the real question is, how did they actually build it? Because the desert wasn't going to make it easy. And it wasn't easy. Not even close, because the Taklamakan didn't just resist this railway, it fought back. And China had to defeat it not once, but 3 times. 3 completely different battles against the same desert, each one on top of the other, each one capable of ending the entire project before the next one even began. The first battle wasn't against distance, it wasn't against heat. It was against the ground itself, because loose desert sand is one of the worst possible foundations you can try to build on. Sand doesn't hold weight the way solid earth does. Its particles are round and smooth, and they slide against each other under pressure. Build on top of it without treating it first, and your structure sinks, tilts, and eventually collapses. Not immediately, but over months and years, the weight drives the sand apart and the whole thing slowly disappears into the desert floor. So before a single pillar could go up, engineers had to transform the sand itself. The first step was hundreds of bulldozers moving across the construction zones, cutting down dunes and redistributing sand to create a level surface, because you can't even begin treating the ground if it isn't even. Every section was checked by surveyors measuring elevation and slope across miles of open desert, making sure the surface was flat and uniform before anything else happened. Then came the water. In a desert with no water, engineers pumped groundwater through long sprinkler arms and underground pipes, injecting controlled amounts of moisture several inches deep into the sand. And here's the physics behind why this works. When you add the right amount of water to dry sand, the moisture creates surface tension between the grains, pulling them together, making them grip each other the way damp flour clumps into a ball. The sand particles, which were sliding freely against each other, suddenly have traction. They bind. The whole mass becomes denser and more cohesive. Once the sand reached the right level of moisture, heavy steel rollers moved in. Massive machines driving back and forth across the surface, compacting it pass by pass, removing air pockets, locking the particles together. Then, dump trucks arrived, pouring loads of reddish earth across the stabilized sand, a base layer that added weight and kept the sand from shifting under heat or vibration. Each layer spread, leveled, and compacted before the next one went down. The whole process repeated, section by section, across hundreds of kilometers of desert. And here's a detail that tells you how serious this environment was. Construction crews couldn't work during the day. The daytime heat was so extreme that concrete cured too fast, sand became dangerously unstable, and machinery constantly overheated. So crews worked at night when temperatures dropped and winds calmed. The entire construction operation ran on a nocturnal schedule, hundreds of machines and thousands of workers moving through the desert darkness, building a railway that the daylight was trying to prevent them from finishing. By the time this process was complete, what had been soft, shifting desert had been transformed into a foundation hard enough to support cranes, concrete mixers, and structures weighing hundreds of tons. And they had done it using nothing but water, weight, and repetition. But that was only the first battle. Once the ground was stable enough to work on, the next challenge was sinking foundations deep enough to actually hold the railway for decades. Because compacted surface sand is one thing, but the weight of an elevated viaduct loaded with freight trains demands something much more permanent. To build each pier foundation, crews had to drill through dozens of feet of loose sand until they hit the solid gravel or compacted soil beneath. That sounds straightforward until you consider what happens when you try to drill a hole through sand. The walls of the hole immediately collapse inward. The sand falls back in and fills whatever you just drilled before you can pour concrete into it. The solution was a technique called bentonite slurry. As the drill bit went down, workers pumped a thick liquid clay mixture into the borehole continuously. This slurry is denser than water and creates pressure against the walls of the hole, holding the sand back while the drilling continues. It's the difference between trying to dig a hole in wet beach sand empty-handed versus using something to hold the walls apart while you work. Once the bore reached solid ground, concrete was poured from the bottom up through trimmy pipes, long tubes that delivered concrete directly to the base of the hole, preventing air pockets that would weaken the foundation. Steel reinforcement cages were lowered in with millimeter precision. 1 degree of tilt in that cage and the pier above it would be compromised. The whole structure above, the girders, the rails, the trains, would eventually be thrown off alignment. And then the piers themselves rose. 11,000 of them, cast using slip-form molds reinforced with galvanized steel and special salt-resistant additives. Because standard concrete exposed to the Taklamakan's corrosive salt-laden winds would start degrading within years. These piers were engineered to last a century in conditions that would destroy ordinary concrete in a decade. The short uniform spans between piers weren't an accident either. Engineers designed them specifically so desert wind would sweep freely beneath the viaduct, carrying drifting sand away before it could accumulate on the trackbed. The railway was designed to use the desert's own wind against it, physics working for the engineers instead of against them, for the first time in this project. As the sun set behind the Kunlun Mountains each evening, those endless lines of pillars stretched toward the horizon, a concrete forest rising from the sand mile after mile, unshaken by the winds howling around them. With 11,000 piers standing and the girders being placed between them, each girder over 100 feet long, weighing hundreds of tons, lifted by crawler cranes and self-launching gantries, aligned with laser systems to within just a few millimeters, the final battle began. laying 890 kilometers of track through the heart of the world's most hostile desert. And they gave themselves 11 months to do it. Here's where the difference between China and America becomes impossible to ignore. In the United States, the overwhelming majority of railway lines are still built using ballast, thick layers of crushed stone laid beneath the rails. That stone layer distributes weight, allows drainage, and absorbs vibration. It's been the standard method for over 150 years. American freight rail runs on it today. China looked at that 150-year-old method and replaced it entirely. On the Taklamakan Railway, the rails aren't sitting on stone. They're fixed directly onto a continuous concrete foundation, a technology called slab track. The rails are aligned using laser systems and installed by automated machinery, then locked permanently into the concrete surface. Instead of loose stones that can shift, wash away, or get buried by sand, the entire structure becomes one unified rigid body. There are no gaps, no loose elements, nothing for the desert to grab onto and displace. This is why Chinese high-speed trains can run smoothly at 350 kilometers per hour, because the surface beneath them is essentially perfect. Perfectly flat, perfectly aligned, perfectly continuous. Meanwhile, if you've ever ridden an American long-distance train, you know the rattling and shaking that comes from a century-old ballast system that shifts a little more every year. Once the concrete slab was down, crews laid steel rails stretching over 260 feet long, lifted by specialized cranes and aligned along the center line with a precision that borders on obsessive. Every joint adjusted for thermal expansion, every fastening clip torqued to exact specification. Workers moved steadily down the line, fitting and tightening, kilometer after kilometer, in the desert heat, or rather, in the desert dark, still working their nocturnal shifts against the sun. And then, the rails were welded, not bolted, welded. Using a process called thermite welding, where a chemical reaction generates temperatures of up to 4,500 degrees Fahrenheit, hot enough to liquefy steel, and fuses two rail ends into one seamless, continuous piece of metal. Repeat that across 890 kilometers, and what you have isn't a collection of individual rail sections. It's a single, unbroken ribbon of steel running from one end of the desert to the other with no joints, no weak points, no places for vibration to build up. After 11 months of continuous work, the rails were down. The testing phase began. Engineering trains ran up and down the route measuring settlement, vibration, rail temperature, and wind-induced sway. The bridges were load-tested with trains weighing thousands of tons. Results showed elevation deviations of only a few millimeters after hundreds of test runs across one of the harshest environments on Earth. Every section is monitored in real time by IoT sensors and solar-powered cameras, data flowing continuously to a central control center. In June 2022, the Hotan-Ruoqiang Railway officially opened, and the world's longest desert railway was completed. Now here's the part that changes everything you just learned, everything you just watched China build. The 11,000 pillars, the decade of desert construction, the 12,000 workers, the $3.5 billion. None of it was primarily about moving passengers. China has fast highways and domestic airlines that already connect these regions. Passenger convenience was never the main driver. This railway was built to extract what's underneath the sand. The Taklamakan Basin sits on top of one of the most significant untapped reserves of rare earth minerals in the world. Neodymium, used in the magnets inside every EV motor and every wind turbine. Lithium, the foundation of every rechargeable battery on the planet. Cobalt, essential for the batteries inside every smartphone, laptop, and electric vehicle. These aren't niche industrial materials. These are the raw materials that the entire technological future runs on. And right now, the country that controls them controls the future. China already produces around 60% of the world's rare earth minerals. That dominance is why, in 2023, when trade tensions escalated, China's threat to restrict rare earth exports sent immediate shockwaves through Western defense and technology industries. American defense contractors quietly started stockpiling. Tech companies started desperately hunting for alternative sources. Because without rare earths, you cannot build the advanced weapons, the chips, the batteries, or the clean energy systems that define 21st century power. This railway doesn't just connect cities. It is a resource extraction corridor, a permanent logistics artery running through the heart of the deposit zone, capable of moving hundreds of thousands of tons of raw materials out of the desert and into China's industrial supply chain. Every kilometer of viaduct that went up was another kilometer of access to minerals that the rest of the world desperately needs and cannot reach. But it goes even further than that. The Taklamakan Loop connects directly into Central Asian trade routes that bypass the sea lanes the U.S. Navy monitors and controls. China's Belt and Road Initiative initiative has been building land corridors across Asia for years, and this railway is a critical inland link, goods, resources, and military logistics moving overland through territories where American naval power is irrelevant. Pentagon analysts flagged this project as a strategic infrastructure concern in defense reports as recently as 2023, not because a railway in a Chinese desert threatens America directly, but because of what it signals. A country that can build a 2,685-kilometer elevated railway through the world's most hostile desert, using its own technology, its own workers, and its own capital, is a country that is broken free of the infrastructure limitations that constrain every other nation on Earth. While America was debating the feasibility of a high-speed rail line between two of its largest cities, China quietly finished a complete railway loop through the deadliest desert on the planet. And then, they started exporting the technology to Saudi Arabia, Pakistan, and Central Africa, turning their engineering solution into a global business, writing the infrastructure blueprint for the next 50 years of global development. That's not just engineering, that's strategy, and most of the world didn't notice until it was already done. Since the railway opened in June 2022, the transformation of the region has been immediate and tangible. Cities like Hotan and Ruoqiang, ancient Silk Road oasis towns that had been essentially cut off from modern China's economic boom for decades, are now directly connected to the national rail network for the first time in their history. Journeys that once meant days of dangerous desert road travel now take hours in air-conditioned carriages. Rare earth extraction from the basin has accelerated. Supply chains that were logistically impossible before the railway opened are now operational. The resources that were locked under the sand for centuries are moving, and the engineering itself has become an export product. The elevated desert viaduct design China developed for the Taklamakan, the salt-resistant concrete, the self-cleaning span geometry, the nocturnal construction methodology, the slab track system, is now being deployed in desert rail projects across the developing world. China didn't just solve its own desert problem. It invented the solution that everyone else will buy for the next 50 years. Here's what that means in plain terms. Every country that needs desert infrastructure, every nation trying to unlock landlocked resources, every government that wants a railway where one has never existed, they're going to call China. Not America, not Europe, China. Because China is the only country on Earth that has actually done it at this scale in these conditions and proven it works. America builds nothing, China builds the world. And then China extracted the rare earth minerals the entire world runs on and handed themselves a permanent logistics advantage that America cannot match, cannot buy, and barely even noticed was happening. And that leaves one question sitting in the air. Do you believe America will ever build infrastructure at this scale again? Or has that window already closed? Let me know what you think in the comments. I read every single one. If this video changed how you see what China is actually building, click the video on your screen right now. Because what China did next will leave you speechless. I'll see you in the next one.